Hello, welcome to my little spiel about various methods of describing solution concentration, mixtures of two different compounds. Let's see. By far and above the most common solvent is water, and also by far and above the most common way to describe how much solute is dissolved in the water is with this description of molarity, which hopefully you remember from your Gen Chem 1 experiences. Molarity is moles of something in liters of solution. So in this example, I'm given 9.65 grams of calcium hypochlorite, a salt that I can weigh on a scale and put in some water. Looks like here they put it that solid into a total liquid of about 750 milliliters, although I don't think I really used 750 milliliters of water, maybe just a little bit less than that, so that the total volume of this dry salt and this water come to, in a volumetric flask, about 750 milliliters. The first thing I think to myself when I see in a question I'm given grams, 9.65 grams of a salt, I go ahead and change it to moles, because this molarity especially requires that we have our solute in moles. So I take 40.1, 16, and 16. There's two of these hypochlorites, and 35.45, 35.45. That all adds up to 143 grams per mole. I put the grams of the molar mass in the bottom, 1 mole in the top, so that the grams of salt cancel the grams in the molar mass. And 9.65 divided by 143 equals the number of moles, as this gram cancels that gram of that salt. Then the next thing to do to find the molarity, the next and last thing to do, is simply to take that 750 milliliters of solution and describe it in liters, and take that 0.0675 moles, compare it to the total volume of the solution, and it looks like 0.750 liters. I have 3 sig figs up here and 3 sig figs here, so I'll leave 3 sig figs in my answer. 0.0900 molar calcium hypochlorite aqueous. Interesting. Before class, you might try one by yourself. 25 grams of magnesium bromide dissolved into enough water to make 355 milliliters of solution. So you could pause the video. I'm not even going to answer it right here, but if you have questions, I'll be happy to look at it with you. Let's try another molarity question, just for the sake of it. What's the molarity of a solution made by dissolving 5.66 grams of manganese 2 nitrate dihydrate in enough water to give 185 milliliters of aqueous solution? So again, I wouldn't probably use 185 milliliters of water, but I'd use like 184 point something. I'm not sure, because this little salt takes up some volume. This 5.66 grams of this salt takes up some volume as well. Well, again, the first thing I hope you'll begin to think to yourself when you see grams is change it to moles, 5.66 grams of this salt. So right here, I changed the 5.66 grams of manganese 2 nitrate dihydrate. 1 manganese, 2 nitrogens, 6 oxygens here, 2 waters here. That all adds up to 214, almost 215 grams per mole. Grams go on the bottom. If I were to divide 5.66 grams by 214.9 grams, I would discover the moles of that salt. But I'm not even done yet. So in my calculation, it's quite common to just draw another big line like this and say, compare it to the total volume, 185 milliliters, 0.185 liters, and my molarity, 0.142. Maybe I ran out of room, but perhaps I should have written this formula, manganese 2 nitrate dihydrate, in back of this to be formally thorough. But that's the molarity of my salt in the water. Another common thing to do with concentrations is to dilute a solution. In diluting a solution, we water it down. We add water to what we already have, therefore making things less concentrated. Here's a question. It says, what's the molarity of a solution created by watering down or adding water to 85 milliliters of 3 molar sulfuric acid to bring in a new volume of 500 milliliters. So I start with 85 milliliters, and I'm going to water down. Looks like I'm going to add about, what would that be, 415 milliliters of water. Although I'm not really counting that. I'm just adding up probably to the line on a volumetric flask. That's the 500 milliliters. 500 milliliter line. But the key point is this. Well, a couple things. This word of in most story problems I've ever seen implies to multiply. So I'm going to take this molarity times this volume, and I'm going to take the molarity of the concentrated times the volume of the concentrated. That would be 3 molar times 85 milliliters. And I'm going to compare that or equate that to the diluted situation where I have 500 milliliters volume is my new volume, and I don't know my new concentration. But I would predict that since I watered things down, this 3 molar would not be as concentrated any longer. It would be watered down to 1 molar or something. No, I don't know. I'll have to do the math. But another key point is this. When I'm watering down, I don't add moles of acid or I don't take moles of acid away. So the moles of acid in the concentrated before situation equals the moles of acid in the diluted afterward situation. So this gives me the moles of the acid concentrated. This gives me the moles of the acid diluted. And the only one I don't know is the new concentration. So the math is pretty simple. Notice I wouldn't really have to change milliliters to liters here, as long as this volume in it is in milliliters as well. The millis will cancel. If I took 3 times 85, I would get the millimoles of acid in this case, which would be the same as this one times this one. It looks like 3 times 85 divided by 500 is 0.51 molar. And yeah, so my new concentration is 0.51 molar. It went down from 3 molar to about 0.51 molar. I call that the watering down equation, the dilution equation. This also works for titrations that are 1-to-1, the stoichiometry of a 1-to-1 reactant to another reactant. It works well in that case, but you have to be careful with that. Let's look at another type of description, not molarity, it's called mass percent. If I have a certain mass of solute and a certain mass of solvent, and therefore I know the total mass altogether, all I have to do is divide the two. So if I had 13.5 grams of a simple sugar, glucose, the formula C6H12O6 really doesn't matter at this point. If my question really is just about the mass percent, all I need is the mass of sugar, 13.5 grams, and the mass of water, 100 grams of water, which is also probably 100 milliliters of water, and I divide the two. This is what's in question. This is my total in the mixture. Although I could think of a situation where I might have more than one or more than 2 components in the mixture. In any case, it's 11.9%. Or, going with that same question, I could say, all right, 13.5 grams of sugar in 100 grams of water. What's the mole fraction? If we compare moles, let me compare moles of sugar to moles of water. No. Moles of sugar to moles total in the mixture. That's the definition of mole fraction. Mole fraction. Well, what do I need? I need moles. So I took 13.5 grams of simple sugar. 6 times 12, 6 times 16, 12 times 1 adds up to 180. That's the molar mass of sugar, this sugar. Put the grams in the bottom. 13.5 divided by 180 gives me 0.075 moles of sugar. I also need to know the moles of water. The total moles of water would be 100 grams of water divided by 18 grams per mole of water. That's 16 plus 1.01, 1.01 adds up to 18.02. Looks like I have quite a bit more solvent than solute. That makes sense. Number one, water is a smaller molecule, so in 100 grams I have quite a bit larger of a quantity of moles as compared to the sugar. But then in my final step for mole fraction, all I have to do is compare the moles of stuff in question to the total number of moles. And it looks like 0.0133 is the mole fraction of sugar in this mixture. This is a fancy letter from the Greek alphabet called chi. It looks like a capital X, a little subscript of whatever compound I'm looking at. Sometimes it's described as mole percent, but usually it's just left as a decimal, even though its name is the mole fraction. The mole fraction of water would be the complement to this. I would add, let's see, this mole fraction plus the mole fraction of water should add up to 1. So it looks like the mole fraction of water would be 0.9867 or something like that, because I only have 2 things in the mixture. Let me go through one more example. And this is another way of describing solution concentration, which is especially important in this chapter that deals eventually with things called colligative properties, and that is molality. Molality starts out similar to molarity, but the denominator is different. Here I have 36.5 grams of naphthalene. It's actually the stuff that they used in old-fashioned mothballs, which I don't think they sell much anymore. And toluene, which smells sort of like model glue of some kind. I have 420 grams of toluene and 36.5 grams of naphthalene. In a later slide, we'll remind you why, a later video clip will remind you why neither this one nor this one would dissolve in water very well. Maybe you already know why this one and this one would not dissolve in water very well, but they look similar to each other, and indeed they would dissolve in each other. So this solute dissolves in this solvent. Here I've included some extra representations of what the bonding in those might look like. If you're into organic chemistry or go on in chemistry, you'll see more of this. This is naphthalene. Again, I have less of this, but I took the naphthalene, 36.5 grams, C10H8. 10 times 12 plus 8 is 128 grams per mole for this stuff. 36.5 grams divided by 128 comes out to 0.285 moles of solute. Now, if I was just describing molarity, I'd try to divide that 0.285 moles of solute by the total volume of the solution. But in this case, I want to do something different. I want to find the molality, which is actually, the numerator is the same, and that's the 0.285 moles. But here in the denominator, we compare not to total volume of solution, but the kilograms of solvent that did the dissolving. And it looks like I had 420 grams of solvent, which is also called 0.4200 kilograms. Let's see, was that, look back up. Yeah, that was 4 sig figs. This is 3 sig figs, but it looks like 420 grams is also 0.42 kilograms. And in any case, it seems like a small difference or a nitpicky difference to worry about the denominator, but there's a reason why we want to compare the moles of solute, the particles of solute, compared to the total mass of stuff that did the dissolving. There are some things called colligative properties where we'll need to know this comparison, and that's called molality. Sometimes written out molality, sometimes little m is molality. At some point, we may be pressed to know the importance that this is not an aqueous solution. This is a solution of naphthalene solute in kilograms of toluene solvent. And they're both solids at room temperature, so we'd have to melt them to get them to mix together. But once they did, we'd have a nice mixture as described by this number. Hey, thanks for watching. Catch you next time.